Uh, I'm not in the robotics, so there's not that much money around. Okay. So this is like a tutorial in convex optimization over quantum states and channels. Most of what I present here is either in some book or should be in some book, but it's just not in one place. So, okay. So let's see. Good. So I will start here. What's a convex set and what's a non-convex set? A non-convex set is one in which you can draw a line such that along the line some point is outside the set. Right? And then, well, density operators form a convex set. The set of Choi matrices, also the same as set of quantum channels, forms a convex set. Great. Well, what's a concave function? Because that's sometimes we want to maximize concave functions, and we see quite a bit of this. So a concave function is something that, for which the line between 2 points along the, if you draw something like that, always lies below the function. And then there are functions that are concave that you see sometimes in quantum information. One is the log likelihood function. So if you do tomography, you see this quite often. And then there's the fidelity. And the fidelity is also a concave function defined over the 2 copies of, say, the set of density operators. And good, so you want to maximize a concave function over the set of, over some convex set. Good. And so as I mentioned, the functions in the previous slide, which was the log likelihood function, you can maximize that over the set of quantum states, so you get the maximum likelihood estimate in tomography. Or if you want to, say, compute the diamond norm of a superoperator, then you can essentially maximize the fidelity function over the set of, over the 2 copies of sort of quantum states, where this L and M operators somehow depend on E and so on. Okay, and then there's more stuff, right? So suppose you want to calculate the capacity of a degradable quantum channel. Turns out that this is a convex optimization problem, so you optimize some function over the set of density operators, and the function that you optimize is convex. Or you want to find the entanglement-assisted capacity, that's also a convex optimization problem, and so you can solve this also. Okay, and so the question is there some straightforward numerical technique that you can use and solve all of this? And the answer is, yeah, you can. And well, the thing is, once you get some answer at the end of your numerical technique, you want to check how close you are to the optimum. And since the problem is convex, you can be confident about your solution, and you can compute this confidence. Okay? And now I'm going to switch. I'm going to move from, say, maximizing concave functions to minimizing convex functions. It's just the same problem, but just one language to just talk about it. Okay, so here's the minimization problem. You want to minimize some convex function over the set of one of the sets I mentioned, density operators or quantum states. And here's the basic algorithm. You break down your problem into many one-dimensional convex optimization problems, and once you kind of stop making progress, you halt. And then you get some solution at the end of this search, and you check how good your solution is. So let's start here. So here's kind of idea 1. Idea 1 is how to first define a one-dimensional problem that you want to solve. You start at some point inside the set. You compute, say, the negative of the gradient direction. And you move along this direction as far as you can until you hit the boundary of the set. And once you hit the boundary, you have defined this line. And that line you use. But in order to do this, you need to just have some oracle that will tell you when you are in the set and when you aren't. So if you can check whether you're in a set, then this kind of ideology is useful. And you can always check whether you're in a set of density operators or quantum channels. It's not difficult to check that. So if I hand you a state, you can do all the checks, right? And now I have a one-dimensional problem along that line. And the one-dimensional problem will look convex. And you can solve this exactly. And you don't even need to do much. You just do a bunch of function evaluations like some sort of golden section search or something. And you can just funnel down to this particular one-dimensional minimum. Yes. That's right. So the functions I'm mostly talking about are differentiable, or you have, some kind of derivative, subgradient, whatever, something like that. And then you just repeat this. So you do this once, and then you get to a new point, and then you do this, and you do this, and then you stop when your function value stops changing. That's the algorithm in this case. And this works if the gradient goes to 0 somewhere inside the set. And if the gradient goes to 0, then you actually also have a certificate of optimality for convex functions. And otherwise, you need some way to kind of explore the solution on the boundary of the set. Because if the gradient is not 0 inside, then maybe the solution of your sort of optimization problem lies at the boundary. And yes. Yes, then the boundary doesn't matter. But imagine like a disk and like a cone function. And I take this cone function, I slightly displace it from the disk, and you want to optimize over the disk. Now the gradient is 0 outside, but the optimum within the disk lies at the boundary. So when you have such a situation, then you want to have to search the boundary. Otherwise, the algorithm that I just stated is good. It will work. Did I answer something? Okay. Okay, good. So now you want, and the question is, does this arise? Actually, this situation arises often, that the solution lies at the boundary of the set that you're interested in. And so you really want some algorithm that will work. And so here's an algorithm, straightforward. You are somewhere at the boundary. You find the negative direction along the gradient, and then you project onto the set. So in order to implement something like this, you need a way to project onto the set that you're interested in. Yes? Not quite, right? Because I project this value back onto the boundary of the set, and the function evaluations only happen on the set. So you don't have to extend. You fix some sort of value and you just move that much, I guess. Yeah, that's like fix a unit value and move that much. That should do it. But now you have to, I go back to the ideology, now I want to define a one-dimensional problem that I can solve. And so I would say, well, you try to search between these 2 points along the boundary. And that's a non-convex problem. So if you have a convex function which is defined on a convex set, but if you try to trace along the boundary of the set, on that boundary the function need not be convex. Does that make sense? Okay. And so good. So this one-dimensional search is non-convex. And so you say, okay, I can't really do it properly maybe, but you use some criteria to find how much you will move. And there's some heuristic about this. So you say, okay, if the function value decreases by a certain amount, I'm gold. And then you move by this amount. The other thing that you can do, and this is an idea I haven't seen elsewhere, is that you try to move along the gradient, but at the point you're on the set, you compute the tangent. And then you project the gradient point onto the tangent. Because all directions that are making you move normal to your convex set are not useful, because they're definitely taking you away from the set and you want to go back. So you just cancel out the normal component. And you project onto the tangent the first time, and then you use this point to scan the boundary by projecting it. And so you can do something like that. Or you can do something else, where you don't have to do projections. So sometimes you're like, projecting is tough, I want some other algorithm for this stuff. Yes? That's right, and for the set of, so you're computing the normal is not always straightforward, and in density operators, you can, in qubit density operators, you know, right, what the normal looks like. It's like a block sphere, so the normal is the radial direction. So there you go. Otherwise, you just try to take some intuition from this, and there's some heuristic. I can tell you how to do that for density operators. So, yeah, so I haven't thought deeply about the STPs, because there the convex set has lots of, so there's all these linear inequality conditions that you have in the STP, because STP is a linear function over symmetric and then inequality constraints. I'm not sure how you compute the normal there. Yeah, there are these inequality constraints. But for density operators, all constraints are equality or positivity. So, yeah. That's right. Well, actually, there's something like you can take any STP that you have and then optimize some function over the set of density operators and give a solution for the STP. There's something like that. So, well, technically, you can use these algorithms to solve STPs, but I don't think you should try that in practice. Like, just use a solver that works for now. And if you get stuck, then, yeah. OK. And so here, well, there's something called the Frank-Wolf direction. So here's the basic idea on how to search, sort of, you want to search along the boundary, but you don't want to do projections onto your set. Suppose they're expensive. What you do is you go to this point and you say, what is the gradient tells me to go outside. OK, that's bad. Why don't I take a direction that has a large overlap with the gradient, such that if I move along that direction, I still remain inside the set? So you say that I take a large overlap of this new direction n with the gradient, such that if I move along this direction, I remain inside this set. So and you find this direction. Sometimes you can find this direction very easily. Otherwise, this itself is a convex optimization problem. But it has a linear objective, so you have some hope that you can sometimes algebraically do it. OK? And now you've defined a new direction, and you have a new line between rho and rho minus d. And you do line search on this, and you just repeat the algorithm I told you. Good. But here's the drawbacks of whatever I told you. So methods 1 and 2 require lots of projections. So if you think projections are expensive or you don't know how to do them, you're kind of stuck. Method 3 does not require projections, but it's not like the most useful way to search the boundary. Because if you go back, you look at the line that's inside the set over which I will be scanning my one-dimensional problem. But I know that the solution is actually at the boundary. So this is not kind of a good way to search on the boundary, but it's close to the boundary that you'll be searching. So it's kind of approximately fine. And if you don't really care too much about the numbers eventually, you just want the solution and some ideas out of it, this also works. OK. And here is actually where I'm not. Yeah, this is kind of a question that I have. How do you really explore the boundaries of these convex sets? And so if you have thought about this or have any ideas, sort of, that would be nice. OK, good. So your algorithm terminates. And now you want to know, well, how well did we perform? And so you want a way to return how close you are to the optimum. So good. So here's how to construct a bound for that. So you have some convex function, and you at some point. And this is your minimum. And so you want to compute this delta. And so what you do is, well, you try to draw a tangent at this point. And you see that the tangent kind of line, and you try to compare the distance, this sort of length, from the tangent to the optimum. This length can be written down easily in terms of the distance of the function from the optimum. So you can write it this way. And the delta is this length, and that's the lower length. And this lower length is always positive from convexity, right? So this gives you a bound on delta. So you compute this quantity called this. Just look at the inner product of the gradient at the point, subtract the with the point minus rho star, but you don't know rho star, right? So this is not yet. You're not quite there. What you really do is you just maximize that thing over the set that you're in. So you maximize a linear function. And this gives you a bound. And this, why is this a good bound? Actually, it equals something called the Frenchel duality, Frenchel dual. And it's called the sub-optimality gap. And when you're at the optimum, you can show that this actually is 0. I'm not showing all of that, but that's true statement. This thing that you computed equals the duality gap, and when this condition called strong duality in convex optimization holds, the thing that I asked you to compute actually equals the minimum duality gap. So it's like, it's a very good way to approximate how well you are, how good you are doing. Otherwise, it's just slightly larger than the duality gap, optimum duality gap, that is. And so good, so you get this number out. But now I told you to compute this number, and you're like, how do I compute that number? And so it's like a linear function over a convex set. For the set of density operators, this has an algebraic solution. And for the set of Choi matrices, you can solve an STP. So at the end of your optimization, you get a solution, you solve a short STP, and you have a certificate of optimality. And that's a good thing, because usually in most problems that convex optimization that we encounter in quantum information, strong duality holds. And strong duality usually holds when you can find a point in the interior of the feasible region. And we usually have a region in which you can find any point in the interior, right? You can find a density operator, a Choi matrix, or something like that. And so strong duality will hold. So you actually, at the end of the algorithm, just get the duality gap, or very good approximation to the duality gap. So, and so that's it. You get all these. You have like a straightforward algorithm for optimizing any convex function over density operators or quantum states. Once the algorithm terminates, you get a good guarantee on your solution. Yes? Yeah, yeah. Yeah, see, the thing is the Choi matrix has a partial trace constraint. And the partial trace constraint makes it sort of difficult to get that algebraic answer. Yeah, I also thought that it should be just, you both should give you an algebraic answer. But yeah, Choi matrices, that's the best I got. Yeah. And yeah, actually you can write down examples where if you think of a non-trivial Choi matrix, the most straightforward case algebraic solution that you would guess is wrong. So it's like, I tried a bit, but eventually it's like, just solve an STP and don't worry about it too much. Okay, good. And now, well, before, because I have quite a bit of time, I think I can show a few examples. Like, yes. No. So the algorithm is an alternative to solving something like, let's see, something like this, where f is not linear. Because if f is linear, you can go to an STP solver and you don't need to even bother about this talk. But if your function is not linear, then you need to work. Yeah, you need gradient information somehow. Yes, yes. So, yeah. Yeah, eventually, right? So everything that I've mentioned is, yeah, you could do an STP for this instead. And maybe log likelihood, I don't think so. But yeah. Yeah, definitely. For this, there's an alternate STP. Because, if you rewrite the STP, the dimensions, I don't know, quadruple or something like that. Actually, not found use for diamond norm operator stuff in my own work, so I didn't bother to check this. But I think, I mean, one day I'll get to get to it, I guess. Yeah, it's something that I wanted to do, to just compare the STP version to this optimization version and see how well they perform. But yeah, okay. So let me try to get an example or two out. And the example is going to be sort of dead simple. So you want to say minimize mod of rho minus A. Rho belongs to your set, right? It's sort of dead easy to do. Actually, you can probably get algebraic answers for this one. But just sort of for the sake of writing a code that works and does what you want it to do, you can do this. So let me try and pull out that code that will. Yes, so C is the set of, so in this example, it's the set of density operators. And A is a symmetric matrix. And so I, in the talk, discussed three solvers, right? So there's a way to do just projections of the gradient, and then you take the tangent along, and then cancel that, and there's the Frank-Wolf direction. So in this example, I'm just looking at the projected gradient one. So this is not a linear function. Maybe you can rewrite it, like put a constraint in and increase the dimension of your problem. Oh, yes, actually, that's right. Okay, well, then this is even more trivial than I thought. Yeah. But nonetheless, I mean, you could, well, so once you write down your algorithm for doing stuff, you just need to change one file which tells you the function and the gradient. And so we can alter that and get more examples. But in this particular example, I just have, say, this function and set of density operators to start with. And so good, I define the problem. I'm just going to, and then I solve it. Let's see what happens. Oops. So I picked the problem in 3x3 complex, 3x3 Hermitian matrices, so just solve pretty fast. But in any case, at the end, you will get, okay, did you converge or not? What's the total time it took? What's the gradient at the final point? And what's the sub-optimality gap I spoke about? And what's the optimal value of the objective function? In this case, the gradient is 0, and which means that actually the optimum lied inside the set, so you don't need to do any projections or something. But let me change that a bit so that the optimum lies outside the set. And then, yeah, that's right. So if you just make A positive semi-definite and trace 1, then this objective function will have 0 value. So it's absolutely like the. But now if you look at the end of this converge to something, and the sub-optimality gap is 10 to the minus 8, good enough for numerical stuff. But the gradient is actually non-zero. So you really needed to search the boundary at some point when you were doing all of this. And you can plot the function values and the objective function and the gradients. You can do exactly the same stuff for Choi matrices. So this is the second file where I do exactly the same thing, but I replace C with the set of Choi matrices. And so you define the problem, you fix the dimensions of the two spaces in Choi matrices that you have, and you start, in this case, I just start with some point. And so the algorithm converged because it couldn't change the function values, and then you compute the norm of the gradient at the final point. It's not 0, so you had to search the boundary. But you can compute the sub-optimality gap, even in this case as an STP, which was done behind the scenes on this one. And then you can sort of solve these problems and so on. And so the function I've taken for these examples is straightforward, but you could write your fidelity function and write the gradient of the fidelity function and compute, say, the diamond norm. So I have examples with log likelihood where, Yeah, I have examples where I do the log likelihood function. And in fact, something more general that you can add a penalty with the log likelihood. And the penalty, yeah. And so yeah, this stuff works for that. But I don't have it in the tutorial today, but it's there somewhere. Yeah. Argument? Yeah, no. That I haven't thought too much about. But I think you would need some assumptions about the function. Yeah, like, but I would say like if your function can have like a large, like it just changes very fast close to the minimum. And then your function, or very slowly to the minimum, but the set in which it changes very fast. So like there's two rubbers, right? The set and the function that you can imagine as rubbers, and changing both will change how the certificate of closeness to the solution at x and closeness to the function value vary with one another. So my guess is you will need some assumptions about the function. Okay, this was quick and short. Okay? All right. Yeah. I should thank the funding agency that sent me here. So this slide is useful. Like, yeah, thank you, the Pittsburgh people, for funding this trip. Okay, good. It's like